Hi, this is lesson 115. So in this lesson, we're going to explore power of complex numbers in polar form by doing investigation number 5, followed by the introduction of the Moivre's theorem. Okay, so let's take a look at investigation number 5. You're going to let Z be R cis theta, use the formula for multiplying two complex numbers in polar form to obtain expressions for z squared, z cubed, power 4, and power 5. You will then generalize the pattern and then answer the conceptual and factual questions below. So pause the video or do the fast forward, and after you're done, investigating, and check your answers. Okay, so based on the investigation, it looks like we have actually found a fast way to find the powers of complex numbers, whether the powers n are positive integers, negative integers, or 0. So what you have actually found is what de Moivre says in the theorem, given that a complex number z is equal to r cis theta, or in Euler's form, r e to the power of I theta, where z is not 0, r belongs to positive real numbers, and also theta belongs to any real numbers, then we can conclude that z to the power of n is equal to r to the power of n cis n theta, or r to the power of n e to the power of I n theta, where n belongs to integers. Okay, so prove that the Moivre's theorem works for n belongs to any natural numbers using the principle of mathematical induction. So here we go. If we let z, the statement that we're going to prove, to be z to the power of n equals to r to the n cis n theta, or r to the n e to the power of I n theta, then the initial case would be the first value of the set of natural numbers at 0. Okay, so let's take a look at the left side. Left side is z to the power of 0, which is 1. The right side, we're going to use, doesn't matter whether we use polar form or Euler's form, r to the power of 0, cis 0 theta. This is really just 1 times cis 0, which is also the real number 1. Okay, as a result, and if you do the same for Euler's form, it will give you the same result. So we can say that P of 0 is true. So the initial case in our proof is true. So next, we're going to assume that if n is equal to k, this is true for some value that k is greater than or equal to 1 and on the set of natural numbers. Then we can rewrite the statement. P of k would be z to the power of k is equal to r to the power of k cis k theta equals to r to the k e to the power of I k theta. Okay, so now we have to look at the inductive step by setting n equals to k plus 1. So what happens here? Well, here we can start by looking at z to the power of k plus 1, which can be broken down or rewritten as z to the power of k times z. So we know the expression of z to the power of k is r to the k cis k theta. We will multiply this by r cis theta. Okay, so multiplying means that we multiply the moduli, so k plus 1, and then we will add the arguments. All right, so here, if I factor theta from the arguments, then I will have k plus 1 times theta, which is a true statement of what we want to prove. Okay, so here P of k, the kth step, does imply the k plus 1 step. Okay, so we can say that since P of 0 is true and P of k does imply P of k plus 1, then by the principle of mathematical induction, P of n is true for all n belongs to the set of natural numbers. Okay, so now we have proven that the de Moivre's theorem works for finding the power of complex numbers. Then we can apply that to some examples. So example 1, write z equals to 1 plus I to the power of 20 in rectangular form. Well, in order to use de Moivre's theorem, we have to first express z in polar form or Euler's form, okay? I'm going to use polar form, which means that I need the magnitude of z, which is 1 squared plus 1 squared square root, that's root 2. And the argument of the complex number 1 plus I, we're talking about in the first quadrant, 1 and 1, so that means that's pi over 4. Okay, so we can now say that, well, 1 plus I to the power of 20 as, you know what, I shouldn't call this z, because that is the power of 20. I should call this 1 plus I. Can be rewritten as square root of 2 cis pi over 4 to the power of 20. Okay, so now we have square root of 2 to the power of 20 for the modulus, and then for cis we have to multiply pi over 4 by 20. Okay, so what does this give me? This is 2 to the power of 1/2 to the power of 20, which is 2 to the power of 10, which is 10^24. And then we have cis of 5 pi, and of course I can simplify 5 pi. So let's think about this. So every 2 pi we go back to the positive x-axis, right? So 5 pi would be the negative x-axis, which is the position of pi. And now let's express this in rectangular form. I have, well, since pi is the position of the negative real axis, this is negative 10^24 plus 0i, so we don't have to write that. Okay. Here is example 2. Find all the powers of z equals to cis of negative pi over 3, where n belongs to the set of integers. And then we're going to represent these numbers obtained on an Argand diagram. Okay. So generally speaking, any powers of z to the power of n, can be represented using, well, the modulus here is 1, so 1 to the n is always 1. Cis negative n pi over 3. Okay, and then for n, that's belong to the set of integers. So we can just start counting, I guess. And we can start from 0, actually. So cis 0, z to the 1 is this negative pi over 3, z squared, cis negative 2 pi over 3, negative 3 pi over 3 or negative pi, 4 pi over 3 negative, 5 pi over 3 negative, set to the 6. The 6th power is going to be cis of negative 6 pi over 3, which is negative 2 pi, right? But negative 2 pi is also the same as 0. And as you can see here then, basically we have reached the end of, you know, a periodic function, so to speak. So there's the powers of z equals to cis of negative pi over 3. We have found that it actually follows a period of 6, right? I should move it over here. So what happens if I have to graph these on an eigenplane? Well, let's take a look. Can't ignore the box there because it's really hiding a grid if I were to teach this lesson in class. Okay, so let's see. We have basically z to the power of 0, z to the power of 1, z to the power of 2, so this is, yeah, something like that, it's good, z to the power of 3, z to the power of 4 is negative 4 pi over 3, so somewhere here maybe. Yeah, this is not exact, but good enough. And then z to the power of 5 would be negative 5 pi over 3, so somewhere here. So all of these positions actually should lie on the circle, okay? I'm not confident that I drew all the numbers, like all the lines properly. Let's see if I can make this work. This is not perfect, is it? Okay, how about this? Hey, it's actually not bad. Okay, so they all follow a circle with a radius of 1, obviously, because that's the modulus of the complex numbers that we're looking at, which is z. And if I label these points, this is z to the power of 0, 1, 2, 3, 4, and then 5 goes. Did I miss one? 0, 1, 2, 3. Oh, 3 is here. Sorry about that. 4 is here. 5, and then we return to z to the power of 6. So automatically we know that z to the power of 7 would just be the same as z to the power of 1, and so on. Okay. And what we also notice is that all of these powers of z are evenly spread out around the circumference of this unit circle. Okay. It's a unit circle because the modulus. And last but not least, we're going to complete another question involving two complex numbers z1 and z2. We're going to evaluate or find what z1 conjugate to the power of 4 times z2 to the power of negative 3 is equal to. Well, since we know that to take the power of complex numbers is the easiest to use the Moivre theorem, we're going to convert z2 into polar form first. Okay, so considering that z2 is 2 root 3 minus 2, so it would be somewhere in the fourth quadrant, its magnitude is what? 2 squared is 4 times 3, 12 plus 2 squared. So the magnitude is square root of 16, which is 4. And then the argument of z2 would be 2. So 1 over root 3 is pi over 6 related. So 2 pi minus pi over 6, which is 11 pi over 6. Or in this case, we can just work out the equivalent of negative pi over 6, which is equally good. So these gives me z2 as 4 cis negative pi over 6. Okay, so let's try to figure out what z1 star conjugate to the power of 4 times z2 to the power of negative 3 actually is. Okay, so we know that the conjugate of a complex number means that we can take the negative of its original argument, and then this is to the power of 4, and then z2, which is 4 cis negative pi over 6 to the power of negative 3. So I'm going to, preserve the powers of 4 because both of these complex numbers have the same moduli. And I can simplify this using exponent laws afterwards, okay? And then for our arguments, we're going to have negative 4 times 5 pi over 3, which is negative 20 pi over 3. And then multiply to the second complex number after I raise it to the power of negative 3. This is going to have 3 pi over 6. Yeah. Plus, because negative negative makes positive. Yep, that's good. So here, simplifying the moduli 4 to the power of 1 is what we have. And then how about the arguments here? I have negative 20 pi, so negative 40 pi plus 3, so negative 37 pi over 6 is what I will have. But this looks way too complicated. So if you recall from previous lessons, we want to keep, the argument within either, all positive from 0 to 2 pi, or keep them between negative pi to positive pi, okay? So let's use the easier version, which is 0 to 2 pi, so plus multiples of 2 pi. And here the closest multiple will be 4 pi, right? Which makes 48 pi over 6. And so this works out to 1, so 11 pi over 6 would be the argument of this result. Okay. So part B of this question says in Cartesian form, give you answers exactly. So that really means that we're going to rewrite for cis 11 pi over 6 in Cartesian or rectangular form. Okay, so this means that I'm going to have for cos 11 pi over 6 plus I sine 11 pi over 6. Like that. So where exactly are we? 11 pi over 6 is 12 pi over 6 minus pi over 6. So we're in quadrant 4. All right, we're right here. That means that cosine is positive, but sine is negative. So pi over 6 cosine would be root 3 over 2. And then minus I times a half. This is going to reduce by 2, 4 reduced by 2, so 2 root 3 minus 2i would be the exact answer in Cartesian form.